Welcome everybody to the third video lecture in week 5. Now we have been studying the induction technique. So till now we have looked at various other proof techniques, namely constructive proof, proof by contradiction, proof by contrapositive, and so on. And we were looking at the very powerful technique called induction. So the idea is, of course, that if you have a problem, we can split up the assumptions into possibly infinite number of subsets, and this will in turn split the problem into an AND of infinitely many problems. Now usually the sub-problems gets indexed by some parameter of the input, and thus the problem A implies B looks like P1 and P2 and so on till infinity. So the problem becomes something of this form, that for all k, prove Pk is true. Now there are many ways of proving this thing. One obvious way is to prove that P1 is true, then P2 is true, and P3 is true, and so on. The only problem is that there are infinitely many subproblems, and hence one cannot expect to solve all of them. So we have to come up with a nice technique of solving all the problems in one go. So the idea is, first prove P1 is true, and then assuming that Pk is true, prove that Pk plus 1 is true. Now if you prove this, we expect that we prove Pn for all n. Why? So P1 is true, so P1 is true implies P2 is true, P2 is true implies P3 is true, P3 is true implies P4 is true, and so on and so forth. But so this with so the fact that this does prove for all n is given by this principle of mathematical induction, which basically states that proving for all k Pk is basically same as first proving P1, and for all k proving Pk implies Pk plus 1. Now this particular mathematical induction, the principle of mathematical induction, has various different versions, and depending on the problem we might have to apply the usual different versions. Now the first version is of course the one that we just now told, which is that if you have to prove that k is greater than or equal to 1, prove that Pk is true. Now here we have first proved the P1 is true, we call it the base case. Then we have the induction hypothesis, which says that let Pk be true for some k. And the inductive step says that, okay, assuming the induction hypothesis, prove that Pk plus 1 is true. And this will prove us the whole thing. Now, if the problem is not asking us to prove for all k greater than or equal to 1, but for all k greater than or equal to some r, the induction hypothesis basically is same, except that we have the base case shifted. Namely, the base case here becomes prove that Pr is true, and the induction hypothesis says again the same thing, that Pk be true, and then prove that Pk plus 1 is true, and that will be good enough. Now sometimes proving that Pk is true implies Pk plus 1 is true might not be that easy. We might be able to prove Pk is true, then Pk plus 2 is true. That might be an easier step to prove. And when that happens, then we have to have a different version. And this version says that first we have to prove Pr, and Pr plus 1 is true. And for any Pk, if we assume that it is true, then prove that Pk plus 2 is true. And this would take care of all the points. The main idea, as I told in many of the course classes till now, is that we have to ensure that all the cases are taken care of. In other words, if this is R and we have to prove for all the things greater than R, so the PR is true, is something maybe the best case, then the inductive step says that PR plus 2 is true. And PR plus 2 is true, then PR plus 4 is true, and so on. But that doesn't take care of the central cases. This case for that. But that R plus 1 case. But that is taken care of by the base case here. And it is not hard to see that if you prove that PR and PR plus 1 is true, then PR plus 2 is true. Since PR plus 1 is true, therefore PR plus 3 is true. Since PR plus 3 is true, therefore PR plus 5 is true, and so on and so forth. So in other words, we can pick any version that would cover all the cases, and that is the most important thing to take care of in induction. Most of them are very intuitive in nature. So for example, here we have this various thing that Pk is true, then Pk plus 2 is true, and then we get the whole thing. Sometimes, unfortunately, we might not be able to prove Pk is true implies Pk plus 2 is true, but maybe something more stronger is required. So here is another technique for that case, that if you can assume that Pk and Pk plus 1 is true, then we can assume the induction hypothesis and prove Pk plus 2 is true. Again, by the same argument, we should be able to cover all the cases. Note that here, the most important thing is that which version to take depends upon what kind of inductive step I can solve, and depending on that, this induction hypothesis gets solved, and depending on that, the base case is solved just to ensure that all the cases are solved. So usually this is the way of choosing the correct version. First, see what can you prove, and then that would ensure various base cases and so on. Sometimes looking at the base cases and the smaller cases might also lead you to choosing the right version. We will be seeing a reasonably complicated problem today in this video lecture, and we will see how to choose the right version. Now, other than these 4 versions, one can come up with many other versions. But then there are also the question that if a problem has more than one parameter, then which parameter to induct on? And we saw in the last video that one can also induct on the multiple parameters. So in fact, this is one of the versions that if you have to prove that for all PQ, some problem that is parameterized by P, Q is true, then one way of going about it is maybe first prove that 1, Q is true, and assuming that P, Q is true, prove that P plus 1, Q is true. And this would take care of all PQ. Now again here, just like the earlier cases, the idea is to ensure that all the possible cases are covered. Here all the possible cases are the 2-dimensional integer grid and not just the integers. And so that has to be taken care of. And there can be various ways of covering all the cases. So here is one more thing that we saw here. First, assume that P of 1, Q is true and P of P, 1 is true. And then if we have P, Q is true, then P plus 1, Q plus 1 is true. Convince yourself that again this technique covers all the cases. Meaning by doing so, for all the PQ greater than or equal to 1, we have P of PQ is true. A third version that we saw an application of last class was again with the same base case, but where we induct not on P or Q but P plus Q. In other words, if P plus Q is less than K, then it is true. Then can we prove that if P prime plus Q prime is K plus 1, then it is true. So here we induct on P plus Q, and again this shows that it can be a valid induction hypothesis or version of induction. There is one more that we saw where we look at the minimum of PQ and we induct on minimum of PQ. Now, given the fact that we have so many versions that are available to us and possibly one can come up with many other versions, let's go back to the same question that we asked. What to induct on, which version to use? A problem can have one parameter, multiple parameters, then which parameter to induct on? One can of course induct on multiple parameters. The main idea is you should always choose a version of induction hypothesis which help us solve the inductive step and ensure that all the cases are covered. So these are the two most important things. Choose the induction hypothesis that help us solve the inductive case easily, and to choose the base case and so on to ensure that all the cases are covered. Now, while this is not necessarily a very easy thing to do of what is the right version to choose, but you can have some better feel of it by doing a lot more problems. So in today's video, let's look at this very interesting problem. It's called the Game inequality. You might have seen this particular inequality stated in your class 12 or class 11 books. What it says is that for all n, meaning if I give you any n positive real numbers, then the average, meaning the summation of ai's by n, is greater than or equal to the nth root of product of a1 to an. This one is known as the arithmetic mean, which is am, and this one is known as the geometric mean, which is gm. And the problem says that arithmetic mean is greater than or equal to geometric mean. I'm sure this was stated in some books or some course in your class 11 or class 12, but it's unlikely that you have seen a proof of this one. So in this video, we will see how to solve or prove this statement. Now, one way of trying to solve any of these problems is by induction. But again, which version of induction to choose, what parameter to choose from. As you can see here, there are many parameters. For example, there is this n, there is this ai's, and so on. Which parameter to use from? So in choosing the correct version, the first thing to note is that identify parameters on which one can induct on. And the most crucial thing is that you can only induct on a parameter that is an integer. You cannot induct on a real number. So the parameters on which to induct must be an integer. Right? So in the Game inequality, there is only one integer, which is the n, the number of ai's. So it's kind of obvious there that we have to induct on that particular n. Now, a good way of starting it is always try the initial cases, meaning case when n equals to 1, 2, 3, 4, 5 and so on. And this would possibly help to identify the correct version to use. And then let's try to prove the kth case by using whatever other cases we need to assume. Meaning, can we prove when n equals to 11 by choosing whatever else? And that will also help us to solve the problem. At the end of the day, we have to ensure that all the cases are satisfied or covered. So for in this problem, it is kind of obvious that we have to induct on n. Good. So if we induct on n, it's not hard to see that the pk or the kth subproblem is for all positive real numbers a1 to ak proves that a1 plus a2 till ak by k is bigger than or equal to kth root of a1 times a2 times dot dot till ak. Right? And thus we have to prove that for all k, pk is true. So this is the problem that clearly splits up into these cases or these various subproblems. Now we should try to see whether we can solve this one for smaller values of k. Can we prove these initial cases, say k equals to 1, k equals to 2, k equals to 3 and so on. So let's start with k equals to 1. And k equals to 1, we have to prove that a1 by 1 is greater than a1 power 1 by 1. And now this is completely trivial. It's very easy to see that it is obviously true. Now let's go to the second one, k equals to 2. Already things are very interesting. How do you prove that a1 plus a2 by 2 is bigger than or equal to square root of a1 times a2? Now, this was something that was given in your assignments and quiz. So let me prove it here again. So the idea is that to prove this statement, it is same as saying I will square on both sides. I get a1 plus a2 whole square by 4 is bigger than a1 a2. And now if I open up the a1 plus a2 whole square, I get a1 square plus a2 square plus twice a1 a2 is bigger than or equal to, let me take this 4 on this side, so I get 4 a1 a2. So this is same as a1 square plus a2 square. Now if I take this 4 to the left, I get minus of a1 a2 greater than 0. And this is of course fine because this is a1 minus a2 whole square greater than 0. And since a1 and a2 are real numbers, so a1 minus a2 is a real number. So a1 minus a2 whole square must be greater than 0. And this is true as a1 and a2 are real numbers. I hope you had proved this one yourself earlier. So this is also one of the applications of the backward proof that we had talked about when we talked about the direct proof techniques. So in other words, okay, k equals to 2 follows not in a not too hard way. Okay, that's one good thing. So we know how to prove that k equals to 2. Now can we prove the k equals to 3 case? So in the k equals to 3 case, we have to prove that a1 plus a2 by 3 is greater than cube root of a1, a2, a3. Of course, what we can do is that now cube both sides and then try to see. Let me leave it to you as an exercise to check that this particular case is not at all easy. This is indeed pretty tough. It is not at all easy to see that one can prove this case. So, okay, k equals to 3, we don't know how to prove at this point, and we still have, of course, no idea which version to choose. Okay, let's moving on. What about k equals to 4? So in k equals to 4, we have to prove that a1 plus a2 plus a3 plus a4 by 4 is greater than 4th root of this thing. Now note that a1 plus a2 plus a3 by 4 can be written as a1 plus a2 by 2 plus a3 plus by a4 by 2 by 2. And this is useful because both these two terms individually looks like the case k equals to 2. So we know that a1 plus a2 by 2 is greater than square root of a1 a2, and a3 plus a4 by 2 is greater than a3 a4. Thus, this quantity, meaning a1 plus a2 plus a3 plus a4 by 4, is greater than square root of a1 a2 plus a3 a4 by 2. Now this is again, this is a real number, square root of a1 a2. This is another real number, a3 a4. So I can apply the case k equals to 2 once again, and I get this equals to square root of these two terms product, which is square root of a1 a2 and a3 a4. And note that square root of a1 a2 times a3 a4 is actually the 4th root of a1 a2 a3 a4, and hence the case k equals to 4 is proved. Now this is not the most easiest way of getting the proof, but this has a nice property. What is it? I have used k equals to 2 in this for proving k equals to 4. So in some sense, what I have proved is that the peak 2 implies p4. Using the 2 case, I can prove p4 case, and I know that p2 is correct. Now convince yourself that what you can solve is actually much stronger. You can solve that pk implies p2k. The same proof technique will go through. So thus we have got some progress. Let's see what we have. Thus, for proving this A and B inequality, we know that k1 and 2 is true, that we know. We have also got that pk is true, then pk plus 2 is true. Sorry, p2k is true. But does it over all the cases? So let's go back to our real line. K equals to 1, I know how to prove. K equals to 2, I know how to prove. Now let's see which all cases I know how to prove. Since I know 2, I know 4 because of k and 2k. Since I know 4, I know 8. Since I know 8, I will know 16 and so on. But still I don't know how to prove k equals to 3. So this is some progress. So what have we proved till now? We have basically proved that for all n, which of this is of the form 2 power k, we can prove that a1 plus till an by n is greater than the product of them power 1 by n. the nth power root of this. So we know that we have not solved for all n, but we have solved for all the powers of 2. We know how to solve pk for all the powers of 2. But we have to now really talk about how do you prove p3. So to understand, let's go back to the k equals to 3 case, and let's see if I can prove p3 using any of the other pk's. So I told you earlier that I don't think that this is a very easy thing to prove directly, but can we use something else? So at this point what we know is that we know that for k equals to 4 we have the solution, which means we have a1 plus a2 plus a3 plus a4 by 4 is greater than 4th root of a1, a2, a3, a4. Can I use k equals to 4 case to prove the k equals to 3 case? The idea here is that let's assume AR equals to A1 plus A2 plus A3 by 3. Now A1, A2, A3, A4 are any real numbers, so I can put anything there. So I put A4 equals to A1 plus A2 plus A3 plus by 3. Note that if I do so, then A1 plus A2 plus A3 plus A4 by 4 does become A1 plus A2 plus A3 by 3. This is something that you need to check. And once I have that, that means I have to prove, we already have, because we know the case of, because we know this thing. So we have a1 plus a2 plus a3 by 3 is greater than 4th root of a1, a2, a3 times the a4. Right? Now this is already good because this left hand side looks very correct, similar to, or actually exactly same as the left hand side that we have to get. But the right hand side is still a bit different. Here you have a 3rd root and here you have a 4th root. But in any case, let's now, so this is the case, which means that I can take 4th power in both sides, and I get a1 plus a2 plus a3 by 4. Whole power 4 is bigger than the product of a1, a2, a3 times a4. I have just taken the 4th root power from both sides. I have just powered both the sides here. Now, once you have that, as you can see, this is a1 plus a2 plus a3 by 4. Sorry, this is actually not 4, this should be 3. I made a mistake here. This is a 3, correct? Because I am taking the 4th power by 3. And this is also a1 plus a2 plus a3 by 3. So this has a 4th power, this has no power. So I can, of course, therefore write it as, again this should be the 3rd power, a1 plus a2 plus a3 by 3 whole cube, which is bigger than a1, a2, a3. And once we have that, now we can take the cube root of both sides and we get, again, this is the 3rd power, a1 plus a2 plus a3 is greater than the cube root of a1, a2, a3. And this is exactly what we wanted to show. Thus, we have been able to prove k equals to 3 case using the k equals to 4 case. Now I leave it to an exercise here that proves that pk, using pk you can prove pk minus 1 case. Just like we have used p4 to prove p3, you can use p8 to prove p7, p7 to prove p6 and so on. Okay, so now where do we stand? So till now we have the case that for k equals to 1 and 2 I know how to solve it. Pk is true, then P2k is true, we saw that one. And now we have that if pk is true, then pk minus 1 is true. Now does it still cover the whole case? All the cases? Let's go back to our line. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now, let me use red dots to identify which of the things I have proved. So, this case says that k equals to 1 is done, k equals to 2 is done. Now, the second one says that, okay, because 2 is done, therefore 4 is done. The third one says that, since 4 is done, therefore 3 is done. Again, since 3 is done, since 4 is done, therefore 8 is done. Since 8 is done, by the third rule, 7 is done. Now since 7 is done, again by third rule, 6 is done. And since 6 is done, again by third rule, 5 is done. Now by second rule, 8 is done, that means 16 is done. And since 16 is done, therefore 15 is done, therefore 14 is done, therefore 13 is done, therefore 12 is done, therefore 11 is done, 10, 9 and all so on. So in other words, this will help us to cover all the cases. It's not the most obvious way of covering all the cases. You first cover all the powers of 2 and then you go backward. This is sometimes known as a backward induction because we are not going from k to k plus 1 necessarily, but we are going from k to 2k and so on, and then going from k to k minus 1. The idea is that this version works perfectly fine because we are able to cover all the cases. So, using this pretty interesting inductive technique, we can now prove that for all n, am is greater than or equal to gn. So, we have seen quite a number of induction versions for solving various problems, mostly in equations and numbers and so on. But induction can also can be used to solve various interesting combinatorial problems. Okay, so we will be seeing one such example in the next video. Thank you.